Chapter 2, Polynomial, Power, and Rational Functions. So with Chapter 2, hopefully it'll start to feel like we're slowing down because Chapter 2 actually doesn't have as much information in it as Chapter 1 did. Chapter 1 was an overview of pretty much 4 different chapters from Algebra 2. Chapter 2, we're kind of overviewing 2 chapters from Algebra 2. In Algebra 2, you spent a chapter looking at quadratic functions, graphing, solving, all the different techniques that have to do with quadratic functions. That's going to be section 1 in this chapter. And then you took a chapter to talk about higher level polynomials, which is going to be what a lot of the rest of this chapter is going to be about. Then at the end of the chapter, we're going to throw in rational functions, but really using all the same techniques that we did in the beginning of the chapter. So to be a little bit more specific, in Chapter 2, Section 1, we're going to look at writing quadratic functions, we're going to look at graphing quadratic functions, we're going to look at applications of quadratic functions. That third bullet, possibly something you did not look at in previous courses, so that probably will be something completely new, although if you have taken physics, it will seem very familiar. In Section 3 and Section 4, which I'm going to lump together as one section, we're going to look at polynomials of higher degree. In other words, we're going to start to look at cubics, quartics, quintics, and so on and so forth. And we're going to look at all the different techniques that you can use to solve polynomial functions. And when I say all the different techniques, I mean all but one main technique, which we're actually going to save for a little bit later in the chapter. Because before we can get to that later technique, we need to remind ourselves about polynomial division. Remember, you covered polynomial division last year in Algebra 2. We're going to talk about long division and synthetic division. And I'm going to talk very briefly about long division because long division is so incredibly useless. As long as you know how to do synthetic division, you can always do synthetic division. You were probably told in your Algebra 2 class that synthetic only applies in certain situations. But I'm going to tell you here how you can actually manipulate whatever situation you're given, whatever the polynomial looks like that you're given. You can manipulate it so that synthetic can be always used. And then once we have polynomial division under our belt, we can finish up talking about solving polynomials of higher degree with our theorems about roots section. We're going to talk about the conjugate pair theorem, and we're going to talk about the rational root theorem. The rational root theorem being the end-all be-all for solving polynomial functions. If nothing else works, try the rational root theorem. Once we know how to solve any polynomial we're given, we'll be ready to actually jump into graphing polynomial functions, which is actually a second look at section 3. When we are graphing any type of function, one of the easiest techniques to figure out what the graph looks like is to start by finding the zeros. So the majority of this chapter is going to focus on finding zeros, and at the end of the chapter we're going to talk about applying that concept of finding zeros to help us graph a polynomial function. And then the last section, rational functions, we're pretty much going to do all the same stuff we did in the first 5 lessons again, but then applying it to rational or fraction functions instead of polynomial functions. So section 1, as good a place to start as any, quadratic functions. So again, last year in Algebra 2, you spent a good chunk of your time talking about quadratic functions, how to factor quadratic functions, how to solve quadratic functions, and how to graph quadratic functions. So the goal here is to simply refresh and remind you how to do all those different techniques with quadratic functions because they come up so often. It's important to have a strong understanding of all the different techniques that come along with quadratic functions. Now specifically we're going to look at writing quadratic functions given at least 2 coordinates on the graph. We're going to talk about graphing quadratic functions from standard form. In chapter 1 we used what's actually called vertex form, which is the parent function paired with transformations. In this chapter we're going to look at graphing quadratics simply from its standard polynomial form. And then at the end of this section, we're going to talk about optimization problems. In other words, these are application problems. What's the highest point? What's the lowest point? What does it take to optimize given certain situations? So we're going to look at that at the end of the section. So real quick, before we jump into anything, let's remind ourselves what a polynomial looks like and what the different classifications of polynomials are. Remember that a polynomial is any time you add or subtract terms together. So a term is really just a coefficient and a variable. Anytime you have a coefficient and a variable multiplied together, that's a term. If you add or subtract terms together, that's a polynomial. So if we just have a single term with no variable, y equals a, where a is some constant value, again, we call that a constant polynomial. As I start adding on terms, we increase the degree of the polynomial. In this case, we've got x to the first power, so that's a linear polynomial. X to the second power makes it a quadratic polynomial. X to the third power makes it a cubic polynomial. X to the fourth power makes it quartic. Easy to remember quartic because it takes 4 quarters to a dollar, or 4 quarts to a gallon. And then if I add a fifth degree term, we have a quintic. Quin meaning 5. So here are just a few examples of some polynomial functions in increasing degree order. Now again, this is just standard form of a polynomial where we list out the terms in decreasing degree order. So I've got the fifth degree term, the fourth degree term, the third degree term, and so on and so forth from left to right. It technically doesn't matter what order you list the terms in, but anytime you're given terms out of order, it's much more helpful to list them in order, because any operations we do, any techniques that we apply to the polynomials typically requires that they be in decreasing degree order. So we have our generic polynomial, where a sub n just represents a generic constant value. N represents the degree. So if this is the highest degree, then this would be 1 degree lower and 1 degree lower, n minus 2, n minus 3, n minus 4, and so on until we run out of variables. And then the a's just represent the constants. So this would be the most generic way I can write a polynomial. So remember, in order to be a polynomial, what's most important is the exponent on the variable. That exponent on the variable has to be a whole number. 0, 1, 2, 3, 4, 5, and so on. You can't have a polynomial with a negative degree. You can't have a polynomial with an irrational degree. You can't have a polynomial with a fraction degree. So as long as the degree is 0 or a positive whole number, then it is a polynomial. Now for the rest of this section, let's refocus our attention just on quadratics. Now when it comes to quadratics, there are two ways or two forms to write your quadratic, just like linear functions have different forms: point slope, slope intercept, standard form. Quadratics have two separate forms, starting with vertex form, which looks like this. Now this should be the form that you're familiar with from chapter 1. So basically this is just if I had y equals x squared, but I have a horizontal shift, I have a vertical shift, and I have a leading coefficient. So we call this the vertex form because, of course, the vertex is just the values of hk. If I know what hk are, then I know where the vertex is. So if I have x minus 2 on the inside and plus 3 on the outside, then I know my vertex is at 2, 3, and then I can graph my quadratic using my odd number pattern with paying close attention to whether the a value is 1 or non-1. Standard form is the standard polynomial form, ax squared plus bx plus c. So if I were to take my vertex form, FOIL out the x minus h, distribute the a, and add k, it would end up looking like this. But notice there's one piece of information between vertex form and standard form that does not change. There is no h in standard form, there is no k in standard form, there's no b or c in vertex form, but there is an a value. That a value in the top and a value in the bottom form, those are the exact same a value. So if the leading coefficient up here is 3, then the leading coefficient in this form, once I simplify it all out, will still be 3. That number is the only number that would not change between the two forms. So let's jump into this by writing an equation of a quadratic with the vertex at -2, -1 through the solution point 0, 3. So I want to write an equation of a quadratic with the known vertex and at least one solution point at the coordinate 0, 3. In other words, you can imagine a quadratic whose vertex is right there, and a solution point just means a point on the graph. So 1, 2, 3, so we have a solution point right here. So we have a parabola that looks something like this, and I want to write an equation for that parabola. Now remember, there are two different forms that I can write the equation in, and just like lines, there are 3 different forms that I can write the equation in, but this doesn't specify which form I'm supposed to use. So I can pretty much use either one, and just like with lines, there's one form that's always easier than the other, and that's going to be vertex form. So you can kind of think of vertex form as very similar to point slope form. Point slope form, y minus y1 equals slope x minus x1. Vertex form is really just the point slope form of quadratics. If I took away the square and moved the k value over to the other side, where k represents a y value, h represents an x value. So this actually is the point slope form. Y minus k equals a represents your slope, x minus h represents your x1. So we're going to start, any time I want to write an equation of a quadratic, we're going to start with vertex form. If the directions say to go all the way to standard form, that's fine, but we're always going to start with vertex form. And one of the reasons why we start with vertex form is that keyword right there. It says vertex right here. The vertex is -2, -1. So I can actually plug in -2 for h, -1 for k. And since 0, 3 is a solution point, I can plug in 0 for the x value and 3 for the y value. So the only thing that's unknown is the a value, which I can now solve for and rewrite my original problem with the a value, the h value, and the k value plugged in. So that's what I'm going to do. So I'm going to solve for a simply by simplifying this equation. We'll start with 0 plus 2 is 2. 2 squared is 4. We'll then add 1, divide by 4, and our a value is 1. So now that I know what the a value is, and I know what my original vertex was, I can rewrite my vertex form with the a value, the h value, the k value plugged in, and here I have my quadratic equation. Now, it's a little bit fancier to label it as f of x instead of y, so that's what I'll do. So here is my final answer, my quadratic equation. F of x equals x plus 2 squared minus 1. Notice I didn't have to write the a value because the a value is 1. You don't have to write a 1. So here's another one. Why don't you try this one your own? Hit play when you're ready. So we'll start this one off the exact same way we did the last one. We'll start with our vertex form. Our vertex this time is the coordinate -3, 2. Our solution point is -1, -6. So we'll plug in h and k where they go. We'll plug in x and y where they go. So here's what it should look like. From here, I'm going to simplify to solve for a. -1 plus 3 is going to be +2. 2 squared is, once again, 4. Then to get a by itself, I will subtract 2, divide by 4. A equals -2. So now I just simply have to rewrite my original vertex form using my new a value and my original h and k value, and I have my final answer. Now, if the question were to ask then, write the equation of the quadratic in standard form, I would follow all these exact same steps just like I do when I'm writing an equation of a line. I would then just simply take this and simplify it further. So I could just FOIL out or square using my shortcut, the x plus 3, distribute the -2, and add 2, and that would put it in standard form. Here's another one for you. Give it a try. As before, start with the vertex form. H is 1, k is -5, x is 3, y is -4. Solve for a. 3 minus 1 is 2. 2 squared, once again, is 4. Add 5, divide by 4, I get 1/4. So here's my a value. My h and k are 1 and -5. Final answer, 1/4 x minus 1 squared minus 5. All right, let's go ahead and move on to graphing quadratics from standard form. So again, we talked about in Chapter 1 how to graph a quadratic using transformations. If I know what the h and the k value are, I can shift it up, down, left, right. The a value tells me whether to stretch it or not. And then, of course, if there's a negative in front of the a, then I know I would flip it upside down if necessary. In standard form, I have slightly different techniques, but it's still a step-by-step process of look for this, look for that, look for that. Now, there are actually two different methods I can use for graphing quadratics in standard form. So option 1 is to start by finding the vertex, which is really the same thing that you're doing when you're graphing in vertex form. Our vertex is the coordinate hk, and in vertex form, the h and the k are explicitly provided to you in the equation. In this form, standard form, ax squared plus bx plus c, not so much. I don't see an h and a k anywhere in the equation, so it takes a little bit more effort to find that vertex, but not too much effort. Hopefully you remember from Algebra 2, there's a handy-dandy little formula. H is simply -b over 2a. If I know the b value and the a value of your quadratic in standard form, I can simply plug it into the formula, and that gives me my h value, or the x value, x coordinate of your vertex. So -b over 2a, hopefully you also recognize -b over 2a as really the first part of the quadratic formula. Basically, if you take the quadratic formula and ignore the square root, you have the vertex formula to find the h of the vertex. So negative b over 2a is the formula we use to find the h, but how do we find the k? Well, there actually is a related formula for finding the k value. Off the top of my head, I think it's something along the lines of c minus b squared over 4a. The point is, it's way too confusing. Who cares about a formula for k? If you know what the h value is, find the k value simply by taking h and plugging it back in to the original function. If you have an x, plug it into the function to figure out the y. So use negative b over 2a to figure out the h, and then figure out the k by simply plugging h back into the original function. It's so much easier. Now from here, again in standard form, we've got our vertex. So then to figure out the rest of the parabola, to figure out where some more coordinates are, we can basically go down our list of useful pieces of information. For any type of graph whatsoever, it's very useful to find x-intercepts, or zeros, which would be these coordinates right here, and a y-intercept, which would be this coordinate right here. Y-intercepts are always super easy to find, especially for polynomials, because if I plug in 0 for x, the only thing that's still there is the c value. So for any polynomial, you can use the trick to find the y-intercept. Just look at the constant value at the end. That's your y-intercept. So this is option 1 for graphing quadratics. It's more of a generic how to graph any function using x-intercepts and y-intercepts, and that's the technique that we're going to be using for most of the polynomial functions in this chapter. But quadratics are special. We don't need all of this information. As long as we know the vertex, we can graph that quadratic using our odd number pattern. That odd number pattern is incredibly useful. Whether you're graphing in vertex form or standard form, once you find that vertex, simply follow the odd number pattern from there to get the rest of the parabola. Let's start with an example. Graph the quadratic. F of x equals negative 4x squared plus 8x plus 3. So, no matter which technique I'm using, the most important piece of information to find is the vertex, so let's find the vertex to start with. I notice that I am in standard form, which means I need my handy-dandy little vertex formula, negative b over 2a. So the b value is 8, so that means negative b would be negative 8, over 2a, and the a value is negative 4. So simply plug and chug from here. 2 times negative 4 is negative 8. Negative 8 over negative 8 is positive 1. So I know my vertex coordinate starts with 1. Now I just need to figure out what the y value is of that vertex simply by taking 1, the h value, plugging it back into the original function to figure out the k value, because if I know the x coordinate, just plug it back into the original function to find the y coordinate. So f of 1, if I plug in 1 for x, I'm going to have negative 4 plus 8 plus 3, or 7. So my vertex is the coordinate 1, 7. And again, I could then take the next step of finding the zeros, finding the y-intercept, but really the only information I need after I found the vertex is the leading coefficient. That leading coefficient is going to tell me what to do after that vertex. First off, it's negative, so I know it's going to be opening down. And the fact that I have a 4 means I'm going to take that original odd number pattern, 1, 3, 5, 7, and I'm going to multiply the entire thing times 4 to figure out what my actual pattern is. So I'm going to start at the coordinate 1, 7. I'm going to open down following a pattern of 4, 12, 20, and I'm definitely not going to need much more after that. So let's do it. We'll start with a vertex of 1, 7. So to the right 1, up 7. 1, 2, 3, 4, 5, 6, 7, all the way up here. And then I follow my odd number pattern opening down, but multiplied times 4. But instead of going down 1 over 1, I'm going to go down 1, 2, 3, 4 over 1 on each side. And notice right here, based on the polynomial, I know my y-intercept should have been positive 3. Following my odd number pattern, I also get my y-intercept of positive 3. So it helps to know those other techniques so you can kind of confirm whichever technique you're using, you can confirm using the other technique. So I go down 4 over 1. My next step would be to go down 12 over 1. Let's see if it fits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I needed 2 more points on my screen. You might have been able to graph it on your graph paper. But once you've run out of space, then we can go ahead and connect the dots. And I have my perfect parabola opening down starting at the vertex of 1, 7. All right, here are a bunch more for you to try. Feel free to try them all at once and then hit play to go through all of them to make sure that you are getting the right answers. Or you can try one at a time and hit play as you go through each one. So once you are ready, either way that you choose, go ahead and hit play. All right, let's look at g of x equals x squared plus 4x plus 3. We'll start by finding our vertex using our vertex formula, negative b over 2a. So the b value is 4. In this case, the a value is 1. So it simplifies to negative 2. So h value of negative 2, plug it back in to get your k value. It's going to be 4 minus 8 plus 3, so we get negative 1. So negative 2, negative 1 is our vertex, and since the a value is 1, we're going to be opening up with our normal odd number pattern. So vertex at negative 2, negative 1, and then opening up with our normal odd number pattern. So up 1 over 1, up 3 over 1, and then my next step would have been up 5 over 1, which it's not going to fit on my screen, but it might fit on your graph paper. So notice I've got a y-intercept of 3, which makes perfect sense. It's exactly what I expected. And in this case, I actually could easily find my x-intercepts simply by by factoring this out. I would get x plus 1, x plus 3 equal to 0. So my x-intercepts will be negative 1 and negative 3. So I could confirm that my x-intercepts are in the correct location simply by solving that quadratic. Connect the dots, and I have my perfect parabola. All right, here's another one for you. If you haven't already tried this, hit pause and hit play when you're ready. If you've already tried this, then keep listening. So we're going to start by finding our vertex using the exact same formula. The b value is 4, the a value is 2. Plug and chug, we get negative 1. Plug in negative 1, so negative 1 squared is going to be a positive 1, but this one's actually going to change the sign, so it ends up being 2 minus 4 plus 2, which is 0. So our vertex is the coordinate negative 1, 0. This time our a value is going to affect our odd number pattern, so instead of 1, 3, 5, it's actually going to be 2, 6, 10, and so on, depending on how much space you have. So the vertex was at negative 1, 0. And then we are going to be opening up, going up 2, going up 6, 1, 2, 3, 4, 5, and I ran out of space on mine, although you may not have. So there is my parabola. Now, interesting note about this one, notice that of course, the y-intercept is what I expected. The x-intercept, if we had done this the other way, finding the x-intercepts by solving 2x squared plus 4x plus 2, if I wanted to solve this to figure out the x-intercepts, first off, everything's even. I could divide everything by 2 to get rid of that common factor. And then when I go to factor this out, factors of 1 that add to 2, well, that's just going to be 1 and 1. And of course, sprinkle in our x's. So I'd actually get x-intercepts of negative 1 and negative 1, which is strange because normally I have two separate x-intercepts, but it's clear based on the graph that it is possible to have only a single x-intercept. We call this a double root. So when I have two of the same solution on an equation, we call that a double root, and that's just a situation where the graph hits the axis but then immediately changes direction. This idea is going to come up again when we start graphing generic polynomial functions that are higher than a quadratic. So when I have a situation of a double root, that tells me graphically that I'm going to hit the x-axis, but I'm not going to cross the x-axis. I'm actually going to just bounce off and turn around. Here's our next one, 3x squared minus 6x. So we find our vertex the same way. Now notice this time there's no constant value. There's usually a constant value on the end there, but that's not a problem. We can still find our vertex using the same techniques because I don't need that constant value to find the vertex. Although it does kind of help you out with some information, there's no constant value, which really means the constant value is 0. And since the constant value is 0, that tells me my y-intercept is at 0. And the fact that the y-intercept is at 0, 0 tells me I also have an x-intercept at 0, 0. So by the time I get to the end of this problem, I expect the graph to be intersecting the origin at 0, 0. So we're going to find our vertex. Same technique, B is -6, B is -6, A is 3. So plug and chug, I get H a value of 1. Plug and chug again, I get my K value of -3. Vertex at 1, -3, leading coefficient of 3. So instead of my odd number pattern 1, 3, 5, it's going to be 3, 9, 15. So vertex at 1, -3, and then I'm going to go up 3. There's my intersection at the origin, and then up 9. 1, 2, 3, 4, 5, 6, 7. I've run out of room, so I will connect the dots. So once again, I can use x and y intercepts to help confirm that this graph is correct. I see my y-intercept is at 0, which is exactly what I expected. And then I can get my x-intercepts simply by setting this equal to 0. Solving for x, you should end up with 0 and 2 as your x-intercepts. All right, let's look at this one. Start off the same way, finding the vertex. I've got -8 as my b value, -2 as my a value. Plug and chug, I get -2 as my h value. Plug and chug again, I get 2 as my k value. So my vertex is at -2, 2. My a value is -2, so instead of my odd number pattern 1, 3, 5, it's going to be 2, 6, 10, but again, the negative means it's opening down. So vertex at -2, 2, and then opening down with a pattern of 2, 6, 10. So down 2, down 6, 1, 2, 3, 4, 5, 6. And then my next step would be down 10, which is probably not going to fit. Confirm y-intercept is at -6. And if I were to solve this and actually get my x-intercepts, I have x-intercepts of -1 and -3, but I don't really need them because I have sufficient information to graph it. All right, here let's look at h of x, 2x squared minus 4x plus 5. Start with the vertex. Vertex h value would be at +1. K value should be at +3. So vertex at 1, 3. And once again, we have a 2 up front. So our odd number pattern, instead of 1, 3, 5, 2, 6, 10. So starting at the vertex of 1, 3. And we're opening up 2, and then my next step would be up 6, but it's not going to fit on mine, so I will connect the dots. Once again, we have our y-intercept at +5, but notice on this one never crosses the x-axis. If you were to attempt to solve this one, set it equal to 0 and solve, first off, it's not going to be factorable. There are no factors of 10 that add to -4. And if you tried the quadratic formula, you'd actually end up with imaginary solutions. An imaginary solution means that there is no real number that makes the function equal to 0. Therefore, there are no x-intercepts. There are no real zeros. So if you were attempting to solve this using your intercepts technique, you would find your y-intercept at +5. X-intercepts would end up being imaginary, which tells you that the graph never actually crosses the x-axis. Now we are ready to move on to optimization, but we're actually going to go ahead and cut off the video here, take a moment to practice what we've learned so far, and we will pick up with optimization next time.